So I'll start by sharing some PowerPoint slides. I will mostly go over PowerPoint slides, but I've also got my tablet ready, and I can share my tablet screen such that I can make some sketches and discuss those in more detail. So that means whenever you've got a question about the slides or the content, then I'm ready to make some more detailed notes about this. So I'll share my PowerPoint slides now. I hope they're coming through. So the lecture course is about correlated electron systems. If you've got any questions later on, you can also email me. There's my email address on here. And the timetable, of course, is that we've got 2 hours today, 2 hours next week, and another 2 hours in 1 more hour in 3 weeks' time. So always Tuesdays morning. We'll do a short break to not sit here for 2 hours continuously, because that will probably be quite tricky to work through. At the end, I'll ask you whether you'd be interested to do some coursework. I can write down some problems and give them to you such that you can work on them in your own time, and you can then submit them maybe 2 or 3 weeks after the lectures end. And if you do so, then of course I'll provide some feedback, mark them. I'm not giving a grade like for course, but to give you some feedback of where you went, where you did things correctly, and how to consider things that didn't work out. Okay, the overview for the course is that I'll start today actually with the first lecture devoted to what's actually not correlated electron systems, but free electron theory, because we will use quite a few of the tools from free electron theory to look at correlated electron materials. And in particular, I'll essentially revise what you've done in your solid state lectures. I assume that you've had some solid state lectures. So I'll revise what we know about Drude theory, transport, Sommerfeld theory, transport and specific heat, and also what we know about magnetic properties like the Pauli susceptibility in metals. Then we're going to go beyond free electron theory in the second lecture today, when we talk about the Fermi liquid theory. This will be more of a pragmatic approach. I understand that there is going to be a lecture course devoted to many-body theory, which Stephen Clark is going to give, and he will certainly work through the Fermi liquid theory in quite much more detail. What I'll do is essentially I'll give a very brief overview of Fermi liquid theory and how it links to the experimental quantities, which those very quantities that I will have discussed already for the first time in the free electron theory, and we will see how they are modified in the Fermi liquid theory. And this will then actually be relevant for some of the coursework that I could provide. And then we will have one lecture that's probably going to be next week, devoted on Kondo effect and heavy fermion materials. One lecture on screening electron-phonon interaction and RKKY interaction. One lecture on quantum phase transitions and non-Fermi liquid behavior at quantum critical points. And in particular, in the Kondo effect and screening, and electron-phonon interaction, we will again link to the experimental quantities that we look at in the first two sections here. And indeed, we do so as well in the quantum phase transitions. Can I ask? I see it. I know you've done your undergrad course in Bristol, so I pretty much know what you've done in your solid state lectures. Makuli, what's your background? Have you done solid state lectures before? Okay, I don't know whether you can hear me. There's a response in the chat. Let me see. You've done some modules in extra. Good. So I guess it probably won't hurt if I go through over a little bit of recap and highlight what's the important bits from free electron theory that are relevant once we look at correlated electron systems. Okay, so There is, of course, also some textbooks out there which you can consult when you've got questions during the course or any point later in your studies. Most important, of course, for the basics that we're going to talk about in terms of free electron behavior, Kittel and Ashcroft-Mermin are good references. Zeeman is also a good reference. Ibach-Lüth is a good reference. They will all have also some details about correlated electron behavior, maybe more on things like electron-phonon coupling and effective masses that occur due to electron-phonon coupling. Singleton is a very good book in terms of thinking about band theory and the resulting electronic properties. Coleman, Introduction to Many-Body Physics, as the title says, will probably be a book much closer to the many-body physics course that Stephen Clark is going to give. But actually, this book contains very good links between the between the free electron behavior, Fermi liquid theory, and what is then relevant for understanding materials like heavy fermion materials, which are a class of very strongly correlated electron materials. Okay, so with that, I'll get started on the free electron theory. So that's essentially not non-correlated behavior, because the starting point is essentially to consider our material as a box, where we've got electrons here sketched in blue, flying around like free gas particles in gas theory do. So that means we treat them as independent. That makes it essentially a non-correlated material. And all we consider is collisions. Actually, that's not quite correct here. One should probably rather say that in the Drude model, we only consider collisions. We don't specify what the collisions are. There's collisions with either electrons with each other or ionic cores. It's actually not really specified, but it doesn't matter. The way the collisions actually enter is that one assumes that there is a typical time scale over which those electrons can fly in a straight line, and then they will scatter their velocity, and in particular the direction of the velocity, completely randomized, and then they start flying in a new direction and maybe subject to things like an electric field, which will of course accelerate the electrons between those scattering events towards the positive electrode. You could also have a magnetic field present, and that will deflect the moving electrons. So the key thing that one gets out of Drude theory is that one can write down that the current in such an free electron gas is given by the number density of electrons times their charge, which is actually minus E, so that's how the minus sign comes about in this equation, times their average velocity. And this average velocity is what we call a drift velocity. That's why that's the reason for the index D here. One can slightly rewrite the velocity, of course, in terms of a momentum divided by mass, and hence one ends up with this equation: carrier density times the charge divided by the mass times the momentum. And in a steady state, one would assume that this momentum is then constant as a function of time. Hence, one can argue that the time derivative of the drift momentum, so that's not the momentum of an individual particle, but it's the average momentum of all particles, that this drift momentum is constant as a function of time. But of course, it will be there will be a component which will give an acceleration due to an electric field. This must now be compensated exactly by scattering events, and these scattering events are captured by assuming that there is a relaxation time tau over which these particles fly in a straight line, and after this time the momentum is essentially completely lost. So that's why this momentum divided by tau shows up here. And from here, it's essentially it's just a little bit of algebra rearranging this equation. We use again that the momentum is of course given as mass times velocity, and hence we can rearrange this for the velocity and then substitute it back into our expression for the current. And because the current, the definition, we can then define a conductivity as a current divided by the applied electric field, and that gives us the very important and basic Drude equation for the conductivity. So we expect that the conductivity is proportional to the charge carrier concentration. Makes sense because more electrons will give you more conductivity, E squared times tau. So that's the scattering time. The longer the time between two scattering events, the larger the conductivity will be, and it's divided by the mass. And this mass is going to be something which we will be looking at a lot when it comes to considering correlated electron behavior, because here is it's here where we capture most of the correlation effect. This Drude formula of the conductivity indeed turns out to be quite successful. In many materials, it describes gives a good description of the overall behavior of the electrical conductivity of materials. And I'm making a forward link here. Of course, we've started in this picture of a gas of electrons, yet we can relate it to the picture that will come up once we look at the Sommerfeld model. Namely, we can relate it to the picture of a Fermi surface. So I assume that you all know that the Fermi surface marks the cutoff in energy or momentum, actually in momentum, sorry, up to which electronic states are occupied and above which they are unoccupied. Now, the reason that this conductivity formula is correct, even once we start taking into account the Fermi surface, namely the Fermi-Dirac statistics, is that whenever you apply an electric field, you displace the whole of the complete Fermi surface. Here, so Kx would be pointing into the right direction. Say an electric field accelerated the electrons into the, sorry, the Kx is of course pointing in the x direction. And say you've got a field applied such that the electrons will be accelerated into the x direction. That will be offset by this scattering after this loss of momentum after a characteristic time tau. So it's not going to be a runaway effect where the Fermi surface continues to be displaced further and further, but it is displaced. And the important bit is that the whole Fermi surface is displaced, and hence all of the electrons contribute to the electrical transport. This displacement, of course, happens by taking away some electrons in a small range of energy on the minus Kx side and adding them on the positive Kx side. But the effect is that the center of the average momentum of the whole Fermi surface is displaced. And we will come back to this when we think about why Drude theory fails for specific heat. Okay, in fact, we'll come back to this on the next slide. So that is named so essentially Drude model is very good in terms of the basic formula of conductivity. And this is the reason, this displacement of the whole Fermi surface is the reason for that. But Drude model, of course, has its failures, and that's why in the next slide we will go beyond this. And the first failure is that the specific heat gives a wrong prediction in the Drude formula, in the Drude theory. In particular, in Drude theory, you would just use the ideal gas equation for the specific heat, which should be 3/2 NKB. That's essentially equipetition. You just divide the thermal energy is going into the three modes that you can have per particle. Hence, N completely shows up here. All of the particles essentially get the same amount of energy from raising the temperature. However, experiment tells us this is not correct. Experiment tells us that the specific heat in metals at low temperatures is much, much smaller than that, orders of magnitude smaller. So what that means is that it tells us that not all the electrons are contributing to the specific heat, and it's only a few electrons that contribute to the specific heat. And again, a link forward, we will look at the details of where the specific heat comes from. But a link forward is now that Here, if you think about specific heat, of course, it's only in a rim around the Fermi surface where particles will be excited, and only they contribute to raising the total energy, and hence only they contribute to the specific heat. We'll go through that in detail, but that's the fundamental difference to the conductivity, where we had the full Fermi surface to contribute to the conductivity. Another failure of the Drude theory is the Hall effect. The Drude theory will tell us essentially you could extend the conductivity theory that I've discussed on the previous slide. You could extend this to include the effect of a magnetic field, and you will come up with this equation that the Hall coefficient, which is proportional to the voltage, the transverse voltage arising under a current and a perpendicular magnetic field in a material. This Hall voltage is equal to the Hall coefficient once you've multiplied it with the thickness and you've divided out the current and the magnetic field. And this Hall coefficient in Drude theory you expect to be equal to 1 over the charge carrier concentration times the charge. Electrons are negatively charged, hence the minus sign, and you expect it to reflect the charge carrier concentration. This is not a complete failure, but what it tells us is that we would certainly not expect any material to display, any metal to display a positive Hall coefficient. We would expect that all metals should be negative Hall coefficient, and it should be just a reflection of how many electrons are free to move around. In reality, experiment does observe materials with a positive sign, and that is clearly in violation with the expectations from Drude theory. The reason for that, and we'll come to that, is that we need to consider the effect of the periodic potential, and we can also consider the effect of correlations, how they change the band structure. We'll come to the band structure, but it's only band structure that will allow us to understand why there can be materials with a charge carrier concentration at difference from the Drude expectation, and in particular why it can have even a positive sign. And it's the curvature in the band structure that will give us this. But we'll come to that on some of the next slides. So essentially, yeah, Drude theory, good for the basic conductivity. We will take forward some of the formalism for the Hall coefficient, but we will have to do something different for the specific heat, and entirely different. So let's start to look at this. And the solution is, of course, the Sommerfeld model. Basics of the Sommerfeld model in contrast to this Drude theory is that now we no longer consider this classical free particles. Rather, we consider the electronic states to be standing waves that have to fit into our material. So we consider our material to be a box of length L, and then the standing waves that we can fit in there have to have vanishing amplitude at the boundaries. So that's our boundary conditions, and hence we can now fit in standing waves with either 0, 1, 2, 3, and so on nodes, and that gives us essentially different momentum for each of those standing waves. Each of those states, so each of those different configurations corresponds to one state. Now, each of those states will occupy a specific space in reciprocal space. It will occupy a specific volume in reciprocal space. You can see how that comes about, because we've got here a length L, and we've got to fit an integer 2 pi in that length L. So that means now these two states, of course, here we fit each time we go up one node, we'll have the integer raised by 1. And that means each state essentially occupies a volume 2 pi divided by L, this length L here. We'll see that on a sketch of the reciprocal space on one of the next slides in more detail. The important bit is that we can now, of course, use this expression, this quantum mechanical expression of the momentum h bar k, to replace the classical expression of the momentum p, and then we can use the same energy equation for to compute the electronic energy for each of those states. And then we start, of course, filling in the lowest energy states, bearing in mind that these are electrons which have to occupy Pauli exclusion principle. And that gives us to start first electron in the lowest energy state, next electron in the next higher energy state, and so on. So we start filling, and we will fill up to all until to the point that all electrons that we have to fill in are in those states. And that brings us exactly to the Fermi energy. So we fill up to the Fermi energy. And at zero energy, that would be, at zero temperature, that would be a sharp cutoff at the Fermi energy, which of course corresponds to a specific momentum as well. At finite temperature, we can capture that some states will be occupied and some states will be partially occupied close to the Fermi energy, and that's captured by the Fermi-Dirac statistics. So let's look at what that gives us for the properties of the materials, and in particular we want to work, of course, towards specific heat and other properties that we can look at in correlated electron materials. Okay, so one of the basics is, of course, that we can now look at this in 3D. So here I've got a sketch of what the Fermi surface looks like in 3D. Namely, we start filling with the lowest momentum states right in the center of that sphere, and we have a cutoff in each direction. Once we reach we've got all the states filled in, and that cutoff is here now the Fermi surface. So we call the surface of the sphere essentially the Fermi surface. Some people will call the volume of that sphere the Fermi surface volume, which is technically a bit misleading a term. Fermi volume sometimes is also used. Now, this can be used to calculate the density of states, which will be a very important quantity. And the way to calculate is by taking the volume of this sphere, which is 4/3 pi kf cubed, and then we've got to multiply it in addition by 2, because in each bit of this Fermi volume we can put 2 electrons, one with spin up, one with spin down. So that's this 2 here in front of the expression, and then we divide it by the volume that each state will occupy. That's 2 pi over L, as I've discussed on the previous slide, for each dimension. And as we considered this here in 3 dimensions, this is cubed. Now, L cubed is of course nothing else but a volume, and hence we can divide both sides of this equation by the volume. So that makes it disappear on the right-hand side of that equation, and will turn the left-hand side into a capital N divided by V, which is the number of electrons divided by V, and hence that's actually equal to a particle density, an electron density in real space. I can see some chat going on. Paul has joined us, and he was confused about the starting time. Okay, I'm sorry, we've started at 9. You can probably, it's been recorded, so if you want, you can catch up on the first half hour later. We've done very fundamentals so far only. So I was just about to explain how we can rearrange this equation. So we've got the particle density on the left-hand side then, and on the right-hand side, apart from some numbers, we will have kf cubed. So it's easy to rearrange this for kf. So we've got here essentially an expression of what the Fermi wave vector will be in the free electron model as a function of electron density. This is important because we can also then rewrite it in terms of an energy. So it's easy to go from kf to an energy, just using the expression that we've had on the previous slide, namely that the energy is equal to h bar k squared over 2m. And hence we could even write this as a function of density, particle density as a function of energy. Maybe I should briefly flick to my tablet screen to go over this, because, or how confident are you guys about deriving the density of states? Because the next step would be one takes this particle density as a function of energy and takes a derivative with respect to energy. And that is what gives this quite important equation of the density of states in 3 dimensions, which has got some numerical prefactors. It has got an h bar in there. It's got the electron mass in there, and most importantly, it's proportional to the energy square root of the energy. Has everybody seen this expression for the density of states in 3 dimensions? Give me a thumbs up if you have. Give me a thumbs down if you didn't. You've not seen this before. Can I see this? Okay, so I get some thumbs up there. So would you know what the density of states looks like in 2 dimensions? See something in the chat. Yeah, Siet says correctly that in 2 dimensions, the density of states is independent of energy. Anybody knows what it would like in 1 dimension? Yeah, 1 over square root E. That's correct. Thank you. Okay, so maybe then let me proceed, and we look at the next bits, because we can now, of course, consider filling in this density of states, which correspond here. It's an area in K space, but actually a better sketch is if we look at density of states versus energy. So you've probably seen plots like this. So that's the square root we've just had on the previous slide. And now I've also, so at low temperatures, you'd expect that you'll fill it right to the Fermi energy. At finite temperatures, you expect that the Fermi-Dirac statistics gives you a smooth function here with some states that are then not occupied here at lower energies that are not occupied, but some states at higher energies occupied instead. Now, this is important because one can see, and of course numerically derive, but also see already what that means for the specific heat. This range over which states are emptied and occupied, the range over which this Fermi-Dirac function smears out the states at the Fermi level, is proportional to the temperature. So more specifically, we've got an area here which is which has a size proportional to kBt, and then its mean value will be raised by kBt to bring those states into those formerly unoccupied states up here. And the larger the temperature, the larger will be this area, but also will be the mean will be going further down, and hence the amount of energy these particles are raised is also going to be larger, proportional to kBt. So what that means in total is that if you calculate the total electric energy, which will be an integral of the energy of each individual particle times the density of states, it will be proportional to the density of states at the Fermi level. So how many states do we have right here? And it will be proportional to T squared, exactly because what I just said, namely that both the area is proportional to T, so that's 1 of the T squared, and the mean value will be going further down, and hence the particles are raised by a larger amount of energy, which is proportional to kBt, so that's the second T in the T squared. So important bit is the electronic energy is proportional to T squared and the density of states. And then it's a small step to think about the specific heat, because that's given by the temperature derivative of the the internal energy. And hence we get an expression that should be proportional to density of states and proportional to temperature. The exact derivation, and that's what Sommerfeld did, is that the electronic contribution to the specific heat should be equal to gamma and times T, and it's pretty much everywhere that gamma is used here for the specific heat coefficient. And this is also known as the Sommerfeld coefficient. You can calculate it or look in some textbook. It's got this numerical value, which you can express, for instance, as pi square over 2 times n, where n is the electron density, kb 1 over the Fermi temperature. Fermi temperature is, of course, given by kbTF equals the Fermi energy. You can rearrange this expression to be expressed in terms of the density of states instead, just using the free energy electron expressions for the Fermi energy and the particle density. So there's various forms how it's given, but the Sommerfeld coefficient is essentially just free electron theory that you need to consider. So all you need is equals h bar squared k squared over 2m, and the space per k state, namely this 2 pi over L. That's all you need in order to convert this into any of the other forms. Okay, so that's the specific heat. Let's see how that works out in experiment. So here is some data, and I have a plot here of the specific heat of potassium. And it's a plot where the specific heat is actually plotted as specific heat divided by temperature versus temperature squared. Everybody confident? Do you guys know why it's plotted this way?
You can read off gamma as the intercept.
That's correct, but why do we bother? What's the slope telling us?
Beta.
Yes, you've looked at these expressions, and the beta. Are you all confident to know where the beta comes from? What's the underlying mechanism? It's essentially the phonons. Of course, I've not talked about these yet, but that's the contribution of the lattice vibrations to the specific heat. We won't bother more about this, but nevertheless, you will find this type of plot many times over in literature. And the reason is that at low temperatures, we expect that there will be an electronic contribution to the specific heat and a lattice contribution to the specific heat. There could also be further magnetic contributions to the specific heat, but let's not concern with this because that's not the standard case. So if there's electrons and lattice contributions, we expect them to be proportional to T and T cubed, respectively. And hence, by dividing this whole equation by temperature, you'll get C over T to be equal some constant plus a beta times T squared. So making this plot C over T versus T squared gives you an intercept and a slope. So you can read off the intercept right here. So here, for instance, the experimental value for potassium, you would read off 2.08. Units are 10 to the minus 3, so millijoule per mole and Kelvin squared. So that's the molar specific heat shown here, and that's the standard to do. So this intercept is gamma, as we said. That's the Sommerfeld coefficient. The experimental value here is 2.08, and if you look at potassium, if you just assume that in potassium, you've got, I think, 1 electron per atom that's freed up. You can measure the density, you know the atomic weight of potassium, so you can calculate what's the number density of potassium atoms in there. And if you then make the assumption it's 1 electron per potassium, you've got the electron density, and hence you can take this expression to compute the expected Sommerfeld coefficient, and the theoretical value you get this way is 1.67. That's a reasonable agreement. It's certainly a lot better than Drude theory would have done, because Drude theory would have told us something about 1,600 or so. So we're close enough to call this a success. And I've deliberately chosen the example of potassium because potassium is, of course, from the part of the periodic table of elements where we expect to observe free electron behavior, namely the first group in the periodic table. So that certainly works out. We will have a brief this thought about later on about what beta means, but actually not so much right now. Let's rather consider again some further successes of the Sommerfeld theory of free of quantum free electrons in metals. One can go about and calculate the electronic conductivity in a similar way to the Drude theory, and one comes up with pretty much the same expression. I've put already an m star on here, but let's not actually. We need to go a little bit further to understand why there's an m star instead of an m here. So let's not worry too much about this. And another important thing that one can calculate now in Sommerfeld theory is the thermal conductivity. And importantly, that's only successful in Sommerfeld theory because it does require a correct theory for the specific heat, as the thermal conductivity is given by the specific heat times essentially the mean momentum transfer. And that turns out to be also proportional to the relaxation time. That's coming in essentially from the momentum conservation or relaxation due to scattering, but it also contains the whole expression that we've had for the specific heat here. And the important bit is now, because we've got the scattering time both in the thermal conductivity and in the electrical conductivity, we can take the ratio of the two, and the the relaxation time will cancel out, and even those masses that we've got in here will cancel out. And hence we expect that the ratio of the thermal to electrical conductivity should be some constants times temperature. And that's what's called the Wiedemann-Franz law, namely that this ratio of thermal to electrical conductivity should be equal to a constant, which is called the Lorentz number, times the temperature. And that's quite a basic property of of free electron theory. It will to some extent survive into Fermi liquid theory, as we shall see. And this is it's an important proof that it's the same particles carrying electrical conductivity and thermal conductivity, or carrying electrical currents and thermal currents. And yeah, this numerical value is often looked at in materials, how it actually confirms with that. So we'll come back later to see how this is justified in real materials. Okay, so that's one property of Sommerfeld theory that we've got. Another property is that we can make a prediction about the temperature dependence of the electrical resistance. So we can say something more about how this tau essentially varies as a function of temperature. And in particular, we can look at how electrons scatter with each other. So for that, let's consider a scattering event. One can display it either as electron in and hole in, and another hole and another electron out. The most important sketch, I think, is this one, where we consider a section of the Fermi surface. That's the solid line here. We consider some initial states, say this unoccupied state, which we could also call a hole, because that's a state below the Fermi energy that's empty. And we consider this occupied state above the Fermi energy. Let's talk about in a minute only why they exist, but let's think about what they can do. They will have to, whenever they scatter into some new states, they will have to fulfill energy conservation, momentum conservation, and charge conservation. That means they can scatter in any new pair of an electron and a hole, an occupied and an unoccupied state, which in total have the same momentum and in total have the same energy. Now, the energy of these two states is given essentially. Yeah, it did cost some energy to create this empty state. This occupied state above the Fermi level. It also did cost some energy to knock out this electron here, and we've got to operate within the same range of energies. So that means these particles will be limited to within these two dashed lines to create some new states. They can't create some states further out because otherwise it would have cost more energy to create those states. So one solution is then to create a new occupied state here and an unoccupied state there, and maybe have some energy going off into a phonon. So because you can see they are closer to the Fermi level, that would be some energy going off or into some other states that are somewhere else on the Fermi sea. Momentum conservation is also something which I've sketched now roughly to be fulfilled here in this sketch, namely between those two states, the blue states, the center of momentum would have been here. Between those two red states, again, center of momentum is about here. So that's fulfilled. And charge conservation is fulfilled by the fact that this is an unoccupied and this is an occupied state. So the same number of electrons are present. So the number, that's of course only one example of states where these two electrons could go to, but they could go to also some states here and there and so on. But clearly they are limited to a number of states that's proportional to the amount of energy that is present, namely the distance between the solid line and the dashed line here. So that's essentially an area that's given here. It's given by the size of the Fermi surface, which is proportional to the density of states, G. And then the number of states available is this volume or this area for the occupied states times this area down here for the unoccupied states, and hence we get a energy square factor into the scattering rate. So the available states determine the magnitude of the scattering rate for such events, and they are proportional. The total scattering rate is proportional to the energy squared, energy relative to the Fermi energy. So it's all about what is the number of initial states, what is the number of final states available, and that determines the total number of the scattering rate. So what that means is that we expect for just the scattering between electrons, occupied and unoccupied states, we expect that this is proportional to energy squared. Now I've already included here a KBT because at a finite temperature we expect that there are occupied states within KBT above the Fermi surface and unoccupied states within KBT below the Fermi surface. That KBT, that area, this cutoff energy, or not a cutoff, but this energy range will grow as temperature grows. It grows linearly with temperature, and hence we can replace this energy here with a temperature. So the scattering rate is hence expected to be proportional to temperature squared. Okay. So we expect that the scattering rate is proportional to temperature squared, and the scattering rate is of course inverse proportional to the lifetime of each individual state, or relaxation time as we've called it before. So we expect that this tau is going to be proportional to the inverse squared of the density of states and the temperature. Now we've had essentially already the conductivity to be proportional to the relaxation rate. In reverse, of course, that means that the resistivity is proportional to 1 over the relaxation rate, and hence this T squared and density of states squared is going to show up as a proportionality in the resistivity. Now, the one thing that we should add before comparing with experiment is that this is, of course, only electron-electron scattering. We also will have electron impurity scattering, which will give us a additional contribution to the scattering probabilities, to the scattering rate, and hence another contribution to the resistivity. So we've got scattering on impurities here marked as rho naught, and we've got this term A times T squared, which marks the electron-electron scattering. Okay, now this prefactor here, we've got it up here, is proportional to this density of states, squared in fact. That means in normal metals like potassium, where the density of states is reasonably small, we will have this coefficient A rather small, in fact, small squared. That means it's very difficult to measure. It's much easier to measure this in materials called heavy fermions, and we'll come to what they are. The important bit is that they have a much larger density of state, sometimes up to a factor of 1,000 larger. And hence this A factor can be raised by even a factor of 10 to the 6. Makes it much more easy to measure. And I've got here one example of the resistivity plotted versus T squared. And you can see the data, at least at low temperatures here, follow reasonably well a straight line. Hence, this T squared is fulfilled. And one could go about reading off this slope to get the A coefficient. And of course, the intercept would correspond to rho naught here. So this is a particular material. We'll come back to this, terbium, rhodium 2, silicon 2 with a little bit of iridium doped in. We'll come back to that later, why this is such a heavy fermion. But the important bit is that this is an example of the resistivity indeed following T squared behavior. And if you've seen yesterday's colloquium in Bristol by Sean Hartnell, you would have seen him also talking about this resistivity temperature squared behavior, which is expected at low temperatures in metals. Do you guys know what you expect from at low temperatures in the resistivity from phonon scattering? So this is all electron-phonon, electron-electron scattering. What do you expect from electron-phonon scattering? Anybody knows? At low temperatures? At high temperatures is probably something that you have learned in school, that electrons have a linear temperature dependent, that metals like copper have a linear temperature dependence of the resistivity, but at low temperatures, one usually expects a T to the 5 in metals due to electron-phonon scattering, and T to the 5 being a smaller power than T squared will be a vanishing term compared to T squared if you just go to low enough temperatures. So that's why asymptotically you do indeed expect this to be present if once the phonons scattering is small enough. Okay, so that's T squared resistivity, which should be another property of another property of Sommerfeld theory, and it will survive in Fermi liquid theory. Okay. Now let's have a look at some magnetic properties, namely the Pauli susceptibility, and that will be there's a few more slides after that, but this way we come essentially already to the end of what we compute in the free electron theory. So the Sommerfeld susceptibility, the Pauli susceptibility is a response of a metal to an external magnetic field. The important ingredient is the Zeeman effect. Electrons with spin up will be raised in a field and spin down will be lowered in a field. Now the change in energy is given by 2 times the magnetic moment times the external magnetic field, because each is raised by, these are raised by mu bar B and these are lowered by mu bar B. Here I've replaced B, the magnetic field, by mu naught H. And I've got the Bohr magneton here. Now, that means we've got some states here raised in energy. They will, of course, be transferred onto lower energy states with the spin down here. And hence, we've got more spin down than spin up electrons. And that's exactly what creates a spin imbalance. And in fact, the spins will be such that the magnetic moments of the electrons are aligned with the external field. Hence, this is paramagnetism. And what you can already see is that we have here an area of states that will be proportional to the density of states. So that's essentially the width of this of a box that you can draw here. And maybe I should actually really draw that in. Let me switch to a pen. So essentially, to understand this, we can here draw a box. And this box then gets transferred over here to fill up states over here. And that's where we then have a majority, more of the spin down states occupied. Now this box has got a width here, density of states, proportional to the density of states, and it has got a height proportional to the magnetic field. So it's just this mu b times b. And that's exactly what we can use to compute then the number of difference of state of spin up and spin down. Now this number difference also is proportional to the total mechanization, because the more spin ups you've got or the more spin downs you've got, the more mechanization you've got in that direction. The important bit is that this density of states factor here is being carried forwards in this mechanization, and hence, because the susceptibility is the derivative of the mechanization, the density of states will be present. Sorry, will be present in the expression for the Pauli susceptibility. There's actually two mu b squared missing here. So important bit: Pauli susceptibility is proportional to the density of states, just as the specific heat and the A coefficient in the resistivity. Okay, so we've got now a few properties for which we've got expectations, how they depend on the density of states, and we'll come back to those in the next lectures. Before we do that, let me have a bit of a look at the Fermi surface, which I've introduced as the free electrons Fermi surface, but how does it look like if we go beyond the free electron model, namely if we go to the nearly free electron model. So free electron model tells us that the energy is given by h bar squared k squared, where k is a vector, of course, over 2m. And here I've made a sketch of what that looks like in the repeated Brillouin zone scheme. So we've got the original dispersion relation, but then we get the same dispersion relation again due to the periodicity of the real space lattice and consequently also of the reciprocal space lattice. We can see some intersection points where the energies of those two branches is degenerate, but actually there's if we now consider the nearly free electron model, it's here where the changes occur, because this is something which maps with the periodicity of the underlying lattice, and hence there will be an interaction strength hybridizing these states, and the consequence is that we open up gaps at these states, at these points in K space, and hence we form bands of energy, energy bands at low energy here, and a new band at high energy, and there's a gap in the states where an energy range has got no allowed states. This is of course related to the fact that you could now have an insulator if you've got a chemical potential lying inside this gap, and a metal if you've got it lying inside the band. We can also see that there's now consequences like a positive curvature down here, which corresponds to the standard electron behavior, a negative curvature up here, which means that the momentum of electron states will actually respond in the opposite direction to an external electric field. And that's exactly where the positive Hall coefficient can come about, because essentially it means that electrons are deflected the wrong way compared to what they would be in the if they are down here, and what they would be doing if it was just a free electron in a metal. So that can explain the Hall coefficient, which I mentioned earlier as a problem of Drude theory. Okay, the more important bit is that this can, of course, also give rise to a Fermi surface. So if you consider this is a 1D example, if you consider it in 3D, you'll get a splitting. So that the blue is the original E squared band. The red is now where the hybridization leads to a lowering of this energy here. And if you then put in a constant Fermi energy, say to intersect somewhere here where it is below those points in the diagonal, but above these points on the faces of this kx and ky axis, then you can stay within the Fermi surface in this direction, but leave it in this direction, and hence you can have Fermi surfaces like looking like this. So we've got we're inside the Fermi surface on the face of this cube, but we leave the Fermi surface towards the diagonals, and hence we can have these Fermi surfaces which are essentially connected spheres along the principal directions. And there's of course more complicated things that are present, and it depends all a lot on the specific structure of a material. This is an example what it looks like in real world. That's the Fermi surface of copper calculated. The important bit is that you've got something which looks like a sphere, but you've got these necks here on the faces of the Brillouin zones joining. There's some measurement methods that can probe these Fermi surfaces. An important one, which I guess you might have heard about, is quantum oscillations, because that can measure, this is essentially the observation of oscillations in properties like the resistivity, where the oscillation period is given by the size of the orbits, and the important one are the extremal orbits, namely here the smallest orbit being the neck and the largest orbit being the belly of this copper Fermi surface. And you can see a small Fermi surface corresponding to that neck, and a large Fermi surface, the fast wiggles here, corresponding to the belly of this Fermi surface. Okay, let me wrap up this first lecture. We've gone from Drude to nearly free electron theory. It's good at explaining electrical transport. It's good at explaining heat capacity, thermal transport, and it gives us a band structure picture which can also explain the Hall coefficient. It gives us this picture of the Fermi surface, and all this is quite successful, and in fact is successfully used in many applications. For instance, in all the semiconductor industry is based pretty much entirely on nearly free electron theory, and barely ever any, there's essentially no correlations that need to be considered. It's quite surprising that this helps, that this works, because so far we've really treated electrons as individual particles, only as single particles. If you write, I've not written really down in Hamiltonian today, but what I've done is I've really essentially populated electron states in this E equals h bar k square over 2m. I've put in individual electrons in this dispersion relation, which without ever considering that these electrons have the same charge and should be interacting via the Coulomb interaction. And in fact, that's surprising, because Coulomb interaction, after all, is quite something strong, in particular at short distances, and one could come to the conclusion that all we've done so far should not work. So the task for the next lecture will be actually to understand why this all works. Actually, it's not just the next lecture, it's the next two that we will need to use to understand why this all works. But before that, I suggest we treat ourselves to a 10-minute break, and we start again in 10 minutes. Do you have any questions so far that you'd like to ask? If that's not the case, then I suggest, there's something in the chat.
So this is just like a, I guess, admin question, but I joined at 9:30 and it looks like you started a bit earlier. So
that's true.
I guess you're starting it, but I mean, in the emails it said this.
I got an email yesterday which said 9 o'clock.
Okay.
I think. But the plan is indeed to start at 9 o'clock each of these Tuesdays.
Okay. So I'll make a note of that.
Feel free to check the recording that will be provided later. Okay, so then I suggest we meet back at 10 past 10 to resume. All right, I'll go and grab a glass of water for me.
Hi, Sven, you're just in your break.
Yes.
Yeah, I'm sorry about the mistake with the start time. It looks like, I checked down here, it looks like I just booked the meeting for the wrong time.
Ah, okay.
Somehow.
So I just followed that booking that you've sent around.
Yeah, I know. I can't understand how I've done that because I was sort of staring at the document as I booked those meetings. But I mean, I can't imagine the system's changed it, but can't really blame the technology. It looks like a simple human error. I just somehow booked it in for 9 a.m. instead of 9:30.
Okay.
Which has caused the confusion. So I'll change the booking. So it's recurring booking for the 3 slots. I've done it for the other 2 as well. Somehow I've booked it all in for 9 a.m. rather than 9:30. I did the ones for Bristol lecturers because Joanna was unable to make Bristol participants co-hosts. She said that's why.
Yes.
That's why we split it, and I did it. Yeah, I seem to have just done it for the wrong time inexplicably, and then also not noticed this morning. So
okay.
It's a shame that somebody else, one of the 2 participants who joined early, didn't. They didn't seem to, because all of the emails basically say 9:30.
Okay. Yeah, I've never looked at the emails. I've always just followed your invite that you sent.
Yeah, well, that's understandable. Yeah, I would do the same. I basically did the same myself this morning when I just saw the thing 9 a.m. Yeah, it's unfortunate for the people that that missed the start of the lecture. I hope it hasn't caused too much inconvenience.
Yeah, I mean, I was doing a recap of things that were mostly part of standard solid state lectures, so it shouldn't be too big a problem. And there's the recording, of course.
Yeah, I mean, yeah, I realize. Yeah, obviously, there's not much I can do about it now apart from apologise to the people who missed the start.
So that means next week we'll start at 9:30.
Yeah. So if you want to reiterate that at the end, I will. As soon as this one's finished, I'll resend. I'll change the start time for all of the other meetings, and so the start time will be 9:30.
Okay.
Tally with the. I mean, people can still join the meeting. I will still start the meeting at like 9:25 or something anyway. But yeah, let's make it 9:30. So, and I will change my bookings to tally with the with all the documents. Yeah. Yeah.
Sure, no problem.
I don't know how I did that. I suppose mistakes happen, but it seems a bit of a bad mistake. But otherwise, you haven't got any other problems at the moment?
No, the rest is all good.
Okay, I'll turn my video off again.
Okay, good. Yeah, I guess maybe one problem for students is that I'm here sitting as a silhouette only because I've got to close my curtain, otherwise I've got the sun on my face.
Well, yeah, it's a kind of a pleasant problem to have. I've got a little bit of a problem, same thing here. I'm sort of kind of partially in. I got my kind of desk in the shade, but the sun shines into this room, which is really pleasant for me.
Yeah.
But then it does, yeah. Sometimes, like you said, if you're in the shade, then I can't see you. But
Siet is asking about the lecture slides. I can, of course, share a copy of those lecture slides. That's absolutely fine. Yeah, I'll do so. What's the best, Tom, to share lecture slides? Do you have a mailing list for all of the students that are in the course?
Yeah, I mean, why don't you, if you want, you can send them to me and I'll send them to because I'll have a list of the participants of this lecture, because we've asked people to register for the Zoom as they enter the Zoom meeting. Then I should have a list of all the participants of this this lecture. I mean,
Paul suggests
the other thing you could do is, I mean, you could just post it in the chat to this, post a link in the chat to this meeting. Equally, I think at the moment, Joanna's just putting the videos on the website as opposed to the slides. Maybe we could do both.
Yeah, I mean, I'm happy to share slides, and Paul actually suggests to have them shared in advance. I'm also happy to do that. Not sure whether I can do that right now. Probably I'll do it. I'll make sure that we've got that for next time.
Yeah, maybe then for next time. Yeah, if you want to send me, I mean, what I can do is, I think Joanna should set up a Google Drive. Let me just check what's on that Google Drive. That's probably going to be the best place. So that's set for.
Okay, I'll just email them to you, and whichever way is the best to communicate with students, I'll leave it.
Yeah, if you send them to me, I can make sure that they've they've been shared with the people that have.
Okay, maybe we should carry on, unless any students would like to make any comments. So we've already discussed now the timetabling. It should be 9:30, and Tom said that this was human error, and we will do it 9:30 next week, and there will be a confirmation email. If anybody has got any remarks about anything else except for the lecture notes and the timing, then now is time. Tom is here to discuss this. Okay, doesn't seem to be the case. So maybe Paul is typing something.
Yes, I was just saying to Sven, I can certainly do that. If Sven sends me the lecture notes in advance, I can circulate to the. I should have a record of the registrants for this lecture through the Zoom Zoom system, and I can, if Sven sends me, I can send out to those people. Obviously, I won't be able to send in advance to any new people from next week's lecture unless I send out to the whole. Unless we send out to everyone, we probably won't do that. But I can certainly send in advance to the people who've registered for this lecture, who've attended this lecture.
Okay.
If I leave the lecture now and plan to just catch up with the notes and the recording and then come for the next lecture, is that going to be okay? Will you still have me registered as a participant?
Yeah, I should have you registered as a participant.
Okay,
yeah.
Thank you. Because I've got such a confusion this morning, I'm going to just leave now and catch up instead and then start again next week.
Yeah, I'm really sorry for the mistake with
the
start time. This seems to be completely my fault.
That's okay. It just got me kind of confused, and so I kind of just lost track of where we were. But it should be easy to catch up if it's just basic solid state stuff. So then I'll come more prepared for next week.
But well, essentially now we're going to start looking at Fermi liquid theory. Do you want to hang around for that?
Okay. Well, I think it would be better if I just revised, because it's some years since I did the solid state, so it may be best I just revise the first one.
Okay. Okay. Sure.
Okay. Thanks then.
All right. So then everybody else will carry on. So next part is about Fermi liquid theory, and yeah, I've put down two textbooks here, which are good resources if you want to read more about this. So we've seen all the successes of the free electron theory, but we've had the big question, how comes it actually works? And the answer is something which actually Fermi liquid theory, attempts to answer. An important piece for Fermi liquid theory was actually the work on helium-3. This is not a metal, obviously. It is a liquid of helium-3 atoms. Now, this is important because helium-3 atoms, the nucleus, so we're talking about the neutral atom here. The nucleus carries 2 protons and 1 neutron. The atomic shell, of course, 2 electrons. So these the electronic shell hence will has a fully occupied shell with no net spin. But the nucleus, of course, has a net spin of 1/2, and that makes it a fermion, and that's exactly why Fermi liquid theory is relevant to understand helium-3. That's probably also where the liquid really originates from. It's also a little bit of contrast to the free electron gas, the free gas theory, the ideal gas theory that we've started to think about for Drude theory. But other than that, I would not get hung up too much on the distinction between liquid and gas here. The important bit is that because helium-3 atoms are fermions, you'd use the very same Fermi-Dirac statistics to treat helium-3 and to describe it. And you'd essentially again start by considering a box where you put in wave functions with an increasing number of nodes from low energy to high energy, and you would have a Fermi momentum cut off, and you would have a Fermi surface for helium-3. What you don't have for helium-3 is a charge. Helium-3 atoms are, of course, neutral, hence there's no electrical conductivity of helium-3. But there is the same sound velocity and the same magnetic susceptibility. There's the same specific heat that you expect for helium-3, like you do for electrons in a free electron metal. Now, the experimental observation is that in helium-3, you can start reasonably well at ambient pressure and low temperatures. So it is, of course, only a liquid at very low temperatures. You need to go, in fact, into a state below a Kelvin to observe the liquid state. Then even lower, there's a superfluid state, but I'm not concerned about this. We're really talking here about the normal liquid. because in the superfluid, what happens there is that two helium-3 atoms will always pair up to form a Bose pair essentially, and undergo a Bose-Einstein condensation. But that's yet a different state. But we're talking here about the normal liquid helium-3 state, where we've got essentially a Fermi surface of helium-3 atoms. Now, the problems that have been quite obvious in helium-3 is that the specific heat, if you apply pressure, increases much more than expected. So on here are the pressures in atmosphere above 1 atmosphere. And what we'd expect is that the specific heat is proportional to the density of states, and hence proportional to the particle density cube root. That's a very weak function of n. So you expect it to increase a little bit initially, but then actually almost level off. Hence, we can see that the specific heat here, which is so this is again a plot of specific heat divided by temperature versus temperature. Here it's not versus temperature squared, because we don't need to worry about a phonon contribution, because there is no lattice of atoms in parallel to the helium-3 atoms. It's just the helium-3 atoms. So this intercept is a direct measure of the Sommerfeld coefficient. And yeah, this argument is what we think about in terms of Sommerfeld coefficient. It should increase initially, but then become a very weak function of the particle density. Now, pressure will, of course, increase the particle density. And we would expect this to rise way not as much as it's present here. So that's what triggered essentially to consider a quantitative theory of describing fermions in more detail. And helium-3 is good because it's reasonably simple a system. It's essentially atoms which don't interact via charge. They only interact via their Pauli exclusion principle and Fermi-Dirac statistics, essentially. So that makes it a reasonably easy to consider system. Okay, so what's the basis of the Fermi liquid theory? So the starting point is, of course, the very same picture that we've had before. You've treated the helium-3 as a sea of particles. You have sketched them essentially as independent gas particles, but underlying that we've got a dispersion relation. Now I'm here drawing this as a hole and electron branch. Maybe let me illustrate where this is coming from. So I'll switch to my pen again. So I've previously, of course, drawn a energy versus momentum relation, which was k squared. So let me see if I can get this right. So it should look, that's meant to be a k squared. And then around the Fermi energy, so that's the Fermi energy now. Around the Fermi energy, if we zoom into this region here, we've got states filled to the Fermi level. So these states are all filled and states empty above. Now, if we want to make an excitation to this state, we can either occupied states, or we can kick a state out down here, which costs us this much of energy here. So this distance, this difference of energy, that's what we've got to pay for kicking out an electron of the occupied states. Kicking out an electron of the occupied states is what we usually call a hole. And it costs us a specific energy. So we could, in terms of energy, we could equally well draw this as a second branch here and mark it as being holes instead of electrons, compared to the electrons that we put into the unoccupied state. So that's exactly how these two branches, a hole branch and an electron branch, show up here in this zoom in of the dispersion relation around the Fermi energy. And I've indeed drawn them here as straight lines, because if the Fermi energy is large compared to the energy scales that we consider, usually we consider temperature, If the Fermi energy is large compared to the temperature, then the curvature of this k squared function doesn't really matter. And this condition EF to be larger than KBT is fulfilled for most materials easily at room temperature. So let's look at these excitations in more detail. So in the free electron theory, we have already considered excitations. We've used that to calculate the specific heat. But what we have not done is how this changes how this changes the energy once we've got the occupation change. So how much does it cost us to put an electron into an unoccupied state? How much does it cost us to remove an electron from an occupied state, or in other words, create a hole? But what we want to ask next is, how is the total system transformed by doing this? What does it do if we put an additional electron into a state up here? What does that do to the Fermi surface? What does that do to all the other particles? So formally, we write this as a we have to write this by considering what happens in terms of the a response to the change to the occupation. So when we do this in a non-interacting way, we essentially say that the energy cost of putting these electrons into a new state costs us h bar k squared minus the Fermi energy or chemical potential times how many ever electrons we have put into those new states or removed from those states. If we want to consider interactions, essentially if we want to consider how is the whole system modified by removing or putting additional electrons, then we've got to consider terms of the order of which are quadratic in the changes of the electron numbers. So electron numbers here, what I've defined as the difference from the equilibrium, namely zero energy, zero temperature occupation of the Fermi, of the nearly free electron theory. Okay, so in the non-interacting case, we've argued that there's a sharp cutoff at zero temperature at the Fermi momentum or Fermi energy. What we'll see is how is this going to be changed once we consider these terms of order delta n squared. And the key theory here for doing so is the Landau theory of Fermi liquids. So, as I said, I'm just going to give a brief overview of how this theory comes about, and I expect that you'll get into much more depth with Stephen Clark in the lectures on the theory of many-body states. So I've said that we capture the energy as a difference. So this is the non-interacting term, which is just energy relative to the Fermi energy or chemical potential times how many electrons you put into those states. Now we are going to consider states being removed at a specific momentum k prime and states removed at a different momentum k. How is that going to change the total energy? That's going to formally depend on some interaction term, which is going to depend on these two different momenta. And yeah, for the total energy, we sum up over all possible combinations of two particle states, essentially. So obviously, we stick to the lowest order. We just consider essentially two particle states and no longer single particle states. But of course, we can hope that this way we capture the leading behavior. Okay, it is essentially, yeah, an expansion in terms of the number of excited states, and it will be certainly valid as long as the deviation from the non-interacting state is small, because then this is of order delta n squared. If that's small, then it's of course smaller than delta n, but it's certainly larger than delta n cubed, and that's why we can cut off this expansion right at after the square term. And the crucial bit are these interaction terms. they capture, actually I should probably go back to laser pointer. They capture how many body states work and what the results are. These interaction terms are essentially at the heart of the Fermi liquid theory. And I'll just give an overview of what they tell us, and I expect that you'll look at these in a bit more detail with Stephen Clark. They are distinguished into symmetric and antisymmetric contributions, and they depend on the spin of the electrons involved. Sorry. So if the two electrons that we were considering are both same spin, then they will be a different coefficient compared to the spins being opposite. More formally, that's in terms of symmetry written down as symmetric and antisymmetric. So this is symmetric and antisymmetric coefficients, which you either add up or subtract. And then these can be decomposed into Legendre factors. Don't worry too much about these details. I'm sure that you'll be looking at this in more detail with Stephen Clark. The connection that I do want to make is how they link with experimental properties. And that's done by further steps. So these coefficients, as we had them here now in the Legendre polynomials, they do link to what's called the dimensionless interaction strength. So they are now essentially relative to the kinetic energy. So these coefficients from the Legendre polynomials, if you multiply them with the sorry, that should be density of states, not so a G in in the way I've written it so far. I can change that, of course. So this should be G instead of N. So density of states times these Legendre polynomials is equal to these interaction strength, and still they carry a symmetric or antisymmetric characteristic, and they will carry a momentum or orbital momentum number L. The important bit is that we can now use these to correct the physical properties that we've calculated so far, and I'm going to just walk you through how they work out. So the specific heat, we've derived the Sommerfeld coefficient before. Here's an expression in terms of the effective mass and the Fermi momentum, which is equivalent to the one that we've had before in terms of the carrier concentration and Fermi temperature. The important bit is here I've now introduced this m star. So m star is an effective mass. And we call it an effective mass because it can deviate from the bare electron mass. We've already seen that this is essentially already true in the band theory, because the curvature of the bands can modify the effective mass, but it gets now further corrections due to the Fermi liquid theory, and in particular this equation here of the correction to the electron effective mass arises as a correction 1 plus this symmetric F1 coefficient from the Fermi liquid theory. So we can see that the effective mass, can be enhanced if this coefficient is positive, and that's entirely only because of many body effects in this Fermi liquid theory. Similarly, the compressibility is an important property that can be modified by the Fermi liquid coefficients, the Landau coefficients. In this case, it's the Fs naught coefficient that will change it. Sound velocity is another one, often in fact looked at in terms of the helium-3 system, because that's something which is easy to study. Another property is the spin susceptibility. That is true for helium-3 atoms and for electrons in metals, as is the specific heat, of course. So the Pauli susceptibility is modified by a different coefficient. It's still this is the original Pauli susceptibility as we've had it in the previous lecture, and now it's modified by 1 plus F naught A. So that's the antisymmetric 0th order Landau coefficient. So the important bit to take away is that each of the physical properties can be described in the terms of a correction from the Fermi liquid theory. And you can see a complete list of this, for instance, in this book by Piers Coleman on many-body physics, and I expect that Stephen Clark is going to go through some of these with you from a theoretical point of view. Coming back to our system of helium-3, one can see that these coefficients, what the values, typical values of these coefficients are. So for instance, down here, I've got a table at a pressure close to ambient pressure. The effective mass is 3.1. So in terms of the bare mass of the helium-3 atoms, so it appears as if these helium-3 atoms are 3 times heavier than they actually are when you've got them separately, when you've got an individual helium-3 atom. And this is all captured within these Fs naught, Fa naught, and Fs1 coefficients, which have got actually quite some sizable values. And because once we compress the helium-3 gas, particles get closer to each other, so they interact even more strongly. And that's reflected here in the fact that the effective mass goes up even higher at a pressure of 27 bar, and so do the Landau coefficients. Right, so Fermi liquid theory is essentially there to describe these corrections. What does it mean? What's happening to the Fermi-Dirac function? In a non-interacting case, we've made the argument that at 0 temperatures, we will have states occupied to the Fermi wave vector, and then we drop to 0, and we've got all states unoccupied above. In the interacting case, that's no longer the case, because here, the energy of an individual particle is modified. So this is the original energy, and it's modified now by the sum of these interaction terms times whatever states you've got. Sorry, that should be a K prime up there. So it's K prime. No, I need to switch to pen again. So it depends on the other states. The energy of state K depends on all the other states K prime and these interaction strengths. So that means now states above the Fermi energy can be lowered in energy, and hence they will become occupied. We have here still plotting them versus K, but they're going to depend on K prime, on states at K prime as well. And that means that we can find that there will be a self-consistent solution where some states are occupied above the Fermi momentum, some states are unoccupied below the Fermi momentum, but it's a little bit different compared to the Fermi-Dirac function. So we've discussed in the case of the free electron metal. So in the non-interacting case, I've discussed that at finite temperatures, we've got this smooth crossover. Let me do that again. Can I erase this? That's not come out well. So I'm better off if I do it like this. It's not so easy to draw on here. So here I've had a smooth function. This is at finite temperature. A smooth function with an inflection point. It's a little bit different in this case of an interacting particle at 0 temperature, because here we still have a section of the new distribution which is perfectly vertical, and this section is what's usually called the quasi-particle weight, and we'll come to that in a second. Why? So this section is the quasi-particle weight Z. It is reduced compared to the quasi-particle weight in the non-interacting case, would be here the full drop from N to 0. Here it's reduced. And it is an important characteristic because only this vertical section can give us still that the specific heat still corresponds to T² behavior. It gives us that the resistivity should follow a T² behavior. It gives us that the Pauli susceptibility should be a constant, and all sorts of other properties really depend on the fact that we've got a vertical section here in the occupation versus momentum, equally in occupation versus energy. So there are modifications, but it's this vertical quasi-particle weight which still gives us some resemblance to the Fermi liquid theory, and that's the ultimate reason why we can write down each of these physical properties as being a modification of the free electron theory, because most importantly, this finite quasi-particle weight guarantees that we still got the T² in the specific heat and a sound velocity and a compressibility. Okay, what does this quasi-particle weight mean? And let me actually start by going into a little bit more of an excursus what quasi-particles mean, because I assume that you might not yet be very familiar with this expression. And in fact, this becomes a little bit of a philosophical discussion. So here I'm starting by looking at a list of possible quasi-particles. You might have heard about phonons. They are quantized lattice vibrations. Has anybody else heard about any of the other quasi-particles in here? Or of any others that I've not listed here? There's of course many more. Is anybody surprised to see that I've put the electron on this list? Somebody's unmuted, but
yeah, electron is fundamental, right?
Electron is of course is a fundamental particle because it does exist as a single particle just in vacuum.
But in a metal it changes, right?
That's exactly it.
Effective mass, whatever.
I would like to make you the distinction between an electron that exists in vacuum and an electron as it exists in a metal. Because once it is in a host metal, it will behave quite differently. We've already made the case that the specific heat of electrons is different from what you'd expect by just pouring electrons in a box of vacuum, namely that it's T² instead of 3½ NKB T. And that's why the fact that we use the same name electron for electrons inside and outside of a metal is a bit misleading, because when we talk about an electron in a metal, really what we mean is a quasi-particle electron, and it corresponds to what excitations are possible exactly on this graph that I've had here with the with a residual quasi-particle weight and some states occupied below and above. The same is true for holes. For holes, it's more obvious that they're not the same like in vacuum, because they've got a different name here, but they are essentially the same type of electronic quasi-particles, only that we assign holes to the states that have a negative curvature in E of k, and hence appear as if one could say that they've got a negative mass, but what's usually done is that this minus sign is rather absorbed into the charge and not into the mass. And that's why these are called holes, because that suggests a positive charge with still a positive mass. And there's of course an awful long list of other quasi-particles. Many of them have some quantization properties. Actually, probably all of them have some kind of quantization, because otherwise we would not call them particle. But let's drill a bit further into why do we call them quasiparticles? And let me make the distinction again. Maybe actually first here's an illustration of what I meant by the electrons. So electronic quasiparticles can live down here where they have an a k-squared dispersion relation, very similar to what they would have in free space. But there could also be states up here where the curvature is quite a bit different, and you can already expect that hence they will have a different effective mass. And here's this region of negative curvature, which then corresponds to whole states. So if the Fermi level lies here, the excitations will be subject to this negative curvature, and hence they will behave as if they have a positive charge instead of the bare electron negative charge. Okay, so with that, as I said, let's think about what does a quasiparticle mean. When we say quasiparticle, we mean essentially a excitation to some system, and it could well be a collective system, like helium, a box of helium-3 atoms close enough together such that they are subject to Fermi-Dirac statistics. The important bit in order to call this a quasiparticle is that this excitation must be reasonably well defined. And by well defined, we mean that in a plot of, you'd call this spectral weight here, or intensity, versus energy, which here I've written as omega, so h bar omega equals an energy, of course. In a plot like this, you've got an increased spectral weight at a specific energy, and that energy is indeed related now to the quasiparticle weight. So let me actually make a sketch about this. Let me actually add here something like let's call this I for an intensity, which is related to, it's just similar to a spectral weight. Now, if we draw the occupation number versus energy, we've made the argument that there will be a finite quasiparticle weight, and that's exactly what produces you a nice peak here. An important bit of a quasiparticle is that the width of this excitation should be smaller than its energy, because the width, of course, is via Heisenberg uncertainty principle related to so the width and energy is related to the lifetime of an excitation. Heisenberg's uncertainty principle essentially tells us delta E times delta T should always be larger or equal times H, or H bar, whichever, doesn't matter. That's just a numerical a small numerical factor. But that means if an excitation becomes more broad in energy, delta E or delta omega goes up, and that means that delta T has to go down. So it becomes much more short-lived, an excitation. And if it's essentially very broad, then it becomes so short-lived that it doesn't make sense to think in terms of an excitation anymore. But if it is long-lived and has a reasonably sharp energy, then we can consider this to be something like a particle, because it carries a specific energy. And in a case of an electron system or a helium-3 system, it also carries some of the other quantum numbers. So in the case of an electron system, if we go back onto this slide, filling it to the Fermi level and then putting a state at a slightly higher energy means that you still have the same charge, E, for that new state. Maybe a different energy, because it's now off that blue line of the free electron behavior, but it still carries the same charge E and the same spin 1/2 like the electron. So it carries some quantum numbers, but it has a different energy, and it behaves a little bit differently, because on this dispersion relation, it has a different effective mass. On top of that, many body effects can change the mass further. So that's ultimately how a quasi-particle, that's ultimately what we should think in terms of a quasi-particle. Now, one can get even a bit more philosophical, because if you consider yourself to be an electron living inside a block of copper, you wouldn't even thinking about outside that that block of copper much, because that's quite a different state. And hence you could define that the array of atomic cores of the copper is essentially your vacuum. So that's why I've made essentially the vacuum is usually denoted as a ket vector with a 0 in there. So defining essentially how you define your vacuum defines whether or not something is called a quasi-particle or a particle. So an electron living in or moving in a block of copper, of course, is just as real as an electron moving outside that block of copper. And you can study just as much elemental physics by looking at electrons in a metallic host than you can do on electrons at in vacuum. And even vacuum, of course, is not just empty. I mean, there's all sorts of effects that add on top of just talk to some particle physicists, and they will tell you that vacuum is not just vacuum, and that particles self-interact, and they interact with particle hole excitations and all sorts of things. And the same is happening essentially to an electron as it moves through a block of copper or some more exotic elements. And it allows us to study inside condensed matter systems quite a few things that are very difficult to access in real particle accelerators or so. And that's also why solid state physics has often been leading some research that later on then was picked up by particle physics. A prominent example is, for instance, the Higgs boson, which of course got the Nobel Prize in, I think, 2015. It was the whole theory of the Higgs boson has its roots in superconductivity, the interaction of electrons and in superconductors and light in superconductors has been studied in the 60s, and there were theories that were written down to see how light essentially acquires a mass in solids in superconductors, and that was later on then generalized to add on relativistic effects, and that's what led to the theory of the Higgs boson and in the end to the discovery of the Higgs boson. And there's many more examples where these quasi-particles that we define in solid state systems to live inside some solid state systems carry some of the important properties that are then studied in particle physics. And often enough, they are easier to access. All right, so that's a bit of a philosophical side of it, but there's also a practical side, because these quasi-particles are the basis of quite a few applications. So previously, I've already said that all the semiconductor industry is based on Fermi-Dirac statistics, but technically, when we talk holes, they are, of course, electronic quasi-particles. So this concept of quasi-particles is essentially already in this basis of semiconductor industry. But then some of the other quasi-particles are also used. For instance, the fluxon is a quantum of flux in a superconducting quantum interference device. So that's used for detection of very small magnetic fields, including those arising from currents in your brain and so on. One can use this to measure these electric currents. And then there's other things like spinon, soliton, skyrmion. So that's a soliton is essentially a wave type packet. A spinon is a spin excitation that is quantized and long-lived. Skyrmion is a topological object of how spins arrange. Essentially, it looks a bit like a three-dimensional wave in the skyrmion, in the spin orientation of inside the material. And all these things have got some suggested applications. The important bit that I wanted to make with this philosophical excursus is that it adds to this discussion of whether we should just be exploring fundamental particles and seek the theory of everything from a particle physics point of view by building the next generation CERN with a larger collider and higher energies and trying to figure out the standard model. The prediction or the promise from some of the particle physicists is that once we've got that theory of everything, we can calculate everything. But the argument is that often enough that might actually not be true, and rather phenomena might be emergent, like the observation that once you have many electrons in a piece of copper, that they behave maybe not anymore like free electrons, but they behave like they acquire a different mass. And when you put in effects like Fermi liquid theory, many-body theory, you get some further modifications of this mass. And of course, over the next lectures, we will be looking at some of the examples of materials classes where these properties are obvious. Okay, I think I'll stop here. I hope I've not confused you too much with this philosophical excursus. The important bit is, of course, that Fermi liquid theory tells us that there is a good reason why we can think about describing many-body theory and still have essentially just a modification to the nearly free electron theory, to the Sommerfeld's theory of metals. Are there any questions? I don't see any for now. So then maybe I'll close for today. And my screen is actually frozen right now. I hope it's not a communication issue. I hear somebody, but I can't see anything actually in my Zoom anymore. Has anybody got any questions? If so, maybe rather tell me than putting in chat. That
so I read like you can think of Fermi liquid theory as adiabatically turning on interactions from a Fermi gas. So how does that like relate to what you've said?
Wow, let me. Oops. No, I think it looks like my Zoom is just playing up. I would like to go back to one of the slides. So I've introduced, of course, the Fermi liquid theory as a quadratic order in the deviations from the ground state. And that's exactly why it's an adiabatic connection, because as you increase this, okay, now Zoom is doing something here. Still frozen. Not sure why. I'd like to go back to one of my slides, but I can't at the moment. It's just showing me the Windows ring of patients circling around.
Yeah, we can't see your screen anymore. So.
Yeah, it says on my side, it says that screen sharing has stopped, but it doesn't even allow me to click OK, because that's just doing nothing. Okay, so I've introduced the correction to the energy. Now something is happening. Can I screen share again? No. Sorry. No, it doesn't come back live. So I have introduced the Landau theory as a correction to the energy with a term sum of k prime times these terms delta nk prime. And as we said that this needs to be a small number, the delta nks, and hence as one increases this deviation from the ground state, the energy correction continuously increases, and that's what makes it adiabatic. So we can consider this to be a there's a direct link from the non-interacting case to the interacting case in the Landau theory. Does that give you a bit of an answer to your question?
Yeah, that makes sense. So
I'm sorry, for me,
small order term.
Yeah, it is a small order term, and importantly, it goes to 0 as these correction coefficients go to 0, and equally as the particle numbers go to 0, or the deviations from the ground state go to 0. And for me, Zoom is still frozen. I can hear you, but I cannot push any button in Zoom. Okay, any more questions? All right, if that's not the case, then I'll leave it here for today. I'll send the slides over to Tom to share with you, and we will resume next week, at 9:30. Okay.
Okay, thanks.
All right. Thanks, everybody.
Thank you.
Bye.
Okay, goodbye. I'll probably have to kill Zoom now on my computer.